We're going to review for exam 4, chapters 14 and 15. And since we had two review documents, one for each chapter, I'm gonna have to go through 14 and then switch to 15. All right. And we got a lab after this too, so we can't dawdle. Let's see, chapter 14. We're going to just start with 1, okay? Which of the following is a conjugate acid-base pair? Remember the definition of you got an acid and a base yields what? Salt and water. Oops, sorry. Wrong topic. We're talking about an acid. This is the true chemical reaction for an acid dissociation in water. So it transfers a proton over to water, and that leaves us with, from the acid, that leaves us with a conjugate base. This is Bronsted-Lowry's definition, plus the hydronium. So notice the requirements for acid conjugate base pair. This part of the molecule must be the same on both sides. Right there. This hydrogen then is the only one that can leave that molecule. So it has to lose one hydrogen at a time. So if we look at each one of these possibilities, if we look at HCl and OCl minus, right? We've got an oxygen in there that wasn't there before, right? So that one can't be it. How about this one? H2SO4, which is an acid, but if it loses one proton, does it end up there? No, that's 2 protons, right? So that one can't be it. And then this one, ammonium ion and ammonia, is that valid? Yeah. You lose one proton from here, what do you have left? You have an ammonia. So C works. Hydronium to OH would have to lose 2 hydrogens. Can't work. And more than one doesn't work. So C has to be the answer for number 1. And the reason I spent so much time on this first one is because understanding the nature of acid dissociation is essential for working the rest of the problems. Let's see, this is getting in my way. There we go. Hydrogen sulfate and bisulfate ion can act as either an acid or a base in water solution. That's a statement of fact. So this is 2. So hydrogen sulfate, or it's also called the bisulfate. That's an older trivial name, the hydrogen bisulfate ion. Can act as either an acid or base in water. Which of the following equations does HSO4 act as an acid? Okay. If it's going to act as an acid, I'm going to use a simplified version here. We're just going to dissociate a proton. Unless they reacted with water. Okay. That takes care of that. There you go. That's the true reaction. So which one of these matches that as an acid? If this loses a proton transferred to water, then you get the hydronium ion and the sulfate. So the only one that looks like it works there is D. Okay. I'm curious, if it acted like a base, what would it be? Right? If water were the acid transferred a proton, you would get H2SO4 plus OH minus. That's if it acted as a base. But the problem asks for an acid. So that one is the answer. D is the answer. This is just speculating. All right, that was 2. Let's see, 3. Which of the following is the equilibrium constant expression for the dissociation of the weak acid HHOCl? Which is what? Acid naming convention. Right? What is this? That's the hypochlorite ion, which means this in aqueous solution is hypochlorous acid. All right, so we're going to use the simplified version. We're just going to dissociate with a proton and what's left over. Okay, so if we write the Ka for this expression, we have the proton, conjugate base, and the undissociated acid. Okay, it looks like A to me. All right, scroll down a little bit, pick up number 6. A solution in which the pOH is 12.1, and we're given pOH equals 12.1, would be described as acidic, neutral, basic. All right. If you don't have an intuition about how pOH works, then we would convert it to pH, right? Just subtract it from 14. That's 9 there and 1 there, right? So now we know that very, very low pH values is very acid. But if you have an intuition about pOHs, you know that very large pOHs would also be acidic, very acidic. Okay? 2 ways to approach that problem. All right, number 7. Number 7. Which of the following indicates the most basic solution? So for this one, we've got some down to E. At least 2 of the solutions are equally basic. Right, that's what E stands for. So how about A? The most basic. If this is the concentration of hydrogen ions at equilibrium, 1 times 10 to the minus 10 molar, then what's the pH? Well, fortunately, that 1 means that let's just do the whole thing. It would be minus the log of 1 times 10 to the minus 10. All right. So what's the log of A times B? The log of A times B is the same as the log of A plus the log of B. So what's the log of 1? 10 to what power equals 1? 0. So that means 0 plus whatever's left over. So what's the log? What's the power of 10 that equals 10 to the minus 10? It's minus 10. Times a minus. So the pH is 10. That's very basic. All right, how was the next one? pOH is 6.7. pOH equals 6.7. That means pH, if we get everything in the same units of measure, then it's easier to compare. So if we convert this one to pH, would be what? 7.3, right? 14 minus 6.7. Right? How about the next one? OH minus. Concentration is 7 times 10 to the minus 5. And now we're going to have to calculate POH, which would be the negative log of that value. Right. Let's see. 7 exponent. Take the log and then change the sign. So I get 5.15, 4.15. POH. And then pH would be equal to 14 minus that. 9.85. Okay, so we got that pH, we got this pH, and we got this pH to compare so far. And then D gives us the pH at 4.2. All right, which one's the most basic? The one with the highest pH value, which would be A. Okay, and since we don't have two of them that are exactly the same, then E can't be true. Okay. All right. Number 8. Which of the following solutions contains the strongest acid? All right. Well, let's see. The first one has a Ka of 6.2 times 10 to the minus 10. That's a very weak acid. The larger the K, the stronger the acid, right? Because the product is in the numerator. And part of that product is hydrogen ion concentration. So the bigger this number, the more hydrogen ions you have, the more acidic it is. So that one's relatively weak. How about the next one? Well, notice that it has 2 protons that can be dissociated. This molecule, H2C6H6O6, which means that, and since the 2 Kas are so far apart, the first one is 10 to the minus 5, the second one is 10 to the minus 12. So which one's going to affect the pH? Only the first one, right? And it's 10 to the minus 5. Right, so the second dissociation has no effect on the pH. The strength of the acid is based on that first one. How about the next one? Well, let's see. I better put this in here. 1.6 times, because the next one has a Ka of 1.8 times 10 to the minus 5. And that's the one we're going to be working with today. Right, that's acetic acid. And then the next one has a Ka of 3.5 times 10 to the minus 8. And the last one, HF, 7.2 times 10 to the minus 4. Okay, which one is the strongest one? This one right here. HF. It's the strongest acid out of that bunch. Now, if we had something else here, like 10 to the minus 12 was down here, then we want to compare these two because they are the next largest ones. 10 to the minus 5, 10 to the minus 5. Then we'd have to go to the coefficient and say, which one is bigger? That one. So in that case, this would be the bigger, the more acidic. But as it is, HF is the more acidic. All right. Next is number 9. Which of the following statements are true? Is or are. Okay, D says at least two of the statements are true. E says all the statements are false. So we've got to look at A, B, and C before we can say anything about D and E. The pH of a strong acid is always lower than the pH of a weak acid. Is that true? What is the pH dependent upon? Negative log of hydrogen ion concentration. That determines the pH. So is it possible? Well, actually, all we have to do is find one exception. Right? What's the pH of HCl when the hydrogen ion concentration is equal to, say the concentration of HCl is, I don't know, 10 to the minus 5 molar. Right, pH of 5. What if you have acetic acid, right? And the calculated hydrogen ion concentration is 10 to the minus 1. Which one has the lower pH? The weaker acid does. Right? So the pH of a strong acid is not always lower than the pH of a weak acid. It depends on the concentration and the Ka. Right? Well, this one doesn't have, essentially is Ka of infinity. Right? But this one has a Ka, we just said is 1.8 times 10 to the minus 5. But the concentration determines the pH, concentration of hydrogen ions. So if we get this acetic acid concentrated enough, we can get the concentration of hydrogen ions up so high that the pH is much lower than hydrochloric acid. So that means A is false. That's not a true statement. How about B? The pH of a solution can never be negative. All right, all we need is one example where it is negative. What if you have a hydrogen ion concentration of 1 molar? Right? Negative log of 1 is what? Well, that's a bad example. Let's make it 2. Right? Negative log of 2. 2 molar. Okay. What's the log of 2? Well, let's see. Log of 2 is 0.3. And then the negative. So there you go. There's one example that blows that statement out of the water. Can never be negative. Well, there it is. It's just a simple calculation based upon the actual hydrogen ion concentration. How about C? For a conjugate acid-base pair, Ka equals 1 divided by Kb. Is that true? No. Right. We determined in class that it's this. Kw divided by Kb. That's Ka. Or Kb is Kw divided by Ka. Either one. So all three of these are false. Right? That's why E is the answer. All three are false statements. All right. How about number 11? For the stepwise dissociation of aqueous H3PO4, which of the following is not a conjugate acid-base pair? And so if we're going to, and what they mean by that, the stepwise dissociation, these are all aqueous, so I'm going to leave aqueous out. All right. The first dissociation is that. 1 minus. Okay. Then we take that product over here and get the next proton. And then we take that one over here and get the third proton. PO or 3 minus. Okay, so that's the stepwise dissociation of phosphoric acid. One proton, second proton, third proton. So which of the following is not a conjugate acid-base pair? All right, what's the acid-base pair for this one? H3PO4 and H2PO4 minus. Is that one in there? Let's see, which of the following is not a conjugate acid-base pair? Well, let's see, let's just start with the A. Yeah, I think that'd be more efficient. C, D, and E. Just check each one and see if it's in here. Right? H2PO4, 2 minus, and PO4, 3 minus. Yep. A is correct. H3PO4 and H2PO4 minus. Yep, there they are. B is correct. H2PO4 minus and HPO4, 2 minus. Yep. C is correct. H2PO4 minus and HPO4, 2 minus. Those are not acid-base pairs, right? Wait a minute. H2PO4, H2PO4 and PO4, 3 minus. That the conjugate base of this one is that, not this. Because to go from here to here, you have to lose 2 protons, right? So this one is false. And we found the one that's wrong. Which is not, okay, oh, well, is this a conjugate acid-base pair? I mean, it's not part. Well, I guess it would be. It could be an acid-base pair. Yeah. But yeah, that's an acid-base pair. Just lose 1 proton, you get a water molecule. The one that's not is D. That's the one that's false. And well, for which of the following 0.1 molar diprotic acids would the second dissociation affect the pH significantly? All right. How do we affect the pH with the second dissociation? The Ka for the second dissociation must be very close to the Ka of the first dissociation, which is very unlikely, but theoretically, is it possible? Well, look at the difference between the Ka of A, 10 to the minus 2, 10 to the minus 7. Right? That's 5 orders of magnitude apart. Right? This second one has no effect on the first one. How about this one? Minus 4, 10 to the minus 8. Okay? That's 4 orders of magnitude apart, no effect. 10 to the minus 4 and 10 to the minus 9. Same thing. The second one is too far. It dissociates too little to have any impact on the first one. So it won't affect the pH. And then D, 10 to the minus 3 and 1.8 times 10 to the minus 3 and 9.3 times 10 to the minus 4. This one is almost 1 times 10 to the minus 3. They are very close to one another. I would think this second dissociation would have an effect on the first one, simply because the Ka is very close to the first one. And the E, the second dissociation, never affects the pH significantly. Can't say never. Right? You cannot say never in this situation, because you need the physical evidence. These values tell you that there is an impact of the second dissociation on the first with this acid. Now, don't ask me what acid would do that, because I can't think of one. all the acids I know, the second dissociation is very far away from the first. But theoretically, D would answer that question. Uh, 16. Okay, which of the following would give the highest pH when dissolved in water to form a 0.1 molar solution? All right, which will give the highest pH? We're looking for highest pH. All right, that is the most basic, which equals most basic. All right, strong acid. Nope. Well, let's put them up here. Strong acid, weak acid, and potassium salt, the weak acid, Ka. And the weak acid is Ha. Ka of weak acid Ha. And then potassium salt, strong acid, Ka, strong acid, Ha. And then the ammonium salt, strong acid. Okay. Since we have salts of acids down here, they are definitely going to give us a higher pH than either a strong acid or a weak acid. So we can ignore these two. What we want to focus on is how do these react? In order to give a high pH, you need to put a strong conjugate base in solution. In other words, what we need is going south on it. What we need is this conjugate base to react with water, right? To take a proton from that water and leave us with hydroxyl. So if this is a strong base, what does that make this? That makes that a weak acid. So the potassium salt of a weak acid would put this in solution without the hydrogen ions. See where I'm going with this? Right, we want to make that out of this. So if we tried it with a strong acid, right, a Ka with a strong acid, this would be a weak base. And you get no return reaction to produce hydroxyls to make the basic solution. So this has to be a weak acid to make the strong base. All right, so the potassium salt of a weak acid is the one that would give the very highest pH or most basic solution. Right? If we had ammonium salt of a strong acid, that's still the strong acid would give us a weak base. So I'm not getting any feedback, so I assume you're either bewildered or you have it pretty well in hand. That's a basic concept in acid-base chemistry. Grasp that concept. How about 19? Solid ammonium acetate. Solid ammonium acetate. C2H3O2. What are we going to do with it? Oh, wait a minute. There's more to it than that. Okay, here we go. Select the answer that best describes an aqueous solution made from each of the following. All right. So if we're going to make an aqueous solution of this, how is it going to behave in solution? Well, all ammonium salts are soluble. So what it's going to do is make this and to that. Okay. Now, how do we need to determine, is this going to be acidic, basic, or neutral? And we're given the Ka and the Kb for each one. The Ka for this one is 5.6 times 10 to the minus 10. And the Kb for this one is also 5.6 times 10 to the minus 10. What that means is they have an equal ability to either produce protons or accept protons. Right? There's an equal competition for protons here. That means you're going to have a neutral solution. Now, if we had a situation where this one was a larger value than that one, right? Say it's 10 to the minus 5 instead of 10 to the minus 10, then this would produce a basic solution because it would strip a proton off of water and take protons from this one as well. But it would produce hydroxyls, and that would be a basic solution. But if this one were larger, it would produce an acidic solution. In this case, they're both equal. So the solution is going to be neutral. There's a competition there. This is Ka, and this is Kb. That gives you an idea about their strength as an acid or as a base. All right. Oh, same deal. Is this going to be basic or acidic? All right, so we've got ammonium perchlorate. Perchlorate. 4, there we go. And this produces ammonium again, where we already have the value for that one. And then the chlorate ion. Good. This one was 10 to the minus 10. 5.6 times 10 to the minus 10. And this one is approximately 10 to the minus 21. All right, this one is significantly larger than that one, which means the acidic reaction is favored. This solution is going to be acidic. The other way you can look at it, oops, sorry about that. That's not supposed to be there. Ammonium perchlorate is this. So the other way you can look at it is with our rule of thumb, right? If this is formed from a weak base, and this is formed from a strong acid, right? Perchloric acid is very, very strong acid, whereas the ammonia is a very weak base. So the rule of thumb says that's strong, that's weak, we have an acidic solution. But this gives you numbers to go by. And all you have to do now is say, what's the competition? Competition is between the acidic and the basic. Right? That's very, very small. This is much larger by 11 orders of magnitude. So we're going to have an acidic solution there. A is the answer. All right. Then we'll go to 22. Which factor listed below is most important in determining the strength of an oxyacid? An oxyacid. Well, we were just looking at the conjugate base of an oxyacid. Right, there's an oxyacid. There's another one in the family, right, like this. And then there's another one in that family, like this, and like that. Okay. How do these acid strengths compare? The strength of the acid increases in that direction. Why? Because of the oxygens. The more oxygens you have in the anion side of the molecule, the stronger it is. So the number of oxygen atoms present in the molecule determines the strength of the acid. And that's simply the effect of electronegativity, right? More oxygens, you have more electron extracting power in this part of the molecule, and it weakens that bond between the chlorine, or between one of the oxygens and the hydrogen. All right, 24. All right, 24. Which of the species below, when dissolved in water, will not produce a basic solution? Not produce a basic solution. E. E is none of these. We're looking for not basic. All right, we have SO2, SO2, we have NH3, we have BaO, and we have BaH2. All right, well, this is definitely basic, right? This is going to dissociate, produce hydroxyl ions. So that's basic, no doubt about it. What's going to happen when you react SO2 with water? What it's going to produce is H2SO3, which is acidic, right? And that's true for any of the non-metal oxides. The non-metal oxides always produce acidic solutions when dissolved in water. Right? Well, there's your answer. A is the answer. But when you react this one with water, what are you going to get? Right? You get ammonium plus hydroxyls. There's basic. When you react this one with water, you get, let's see, barium. Oh, you get this compound right here. The metal oxides always produce basic solutions, and the non-metal oxides always produce acidic solutions. Right, so A is the answer. All right. And we're going to bring Lewis into this discussion. Lewis acids and bases. Which of the following species cannot act as a Lewis base? All right, here's the way I reason this one out. If Bronsted-Lowry, we get that definition for acids and bases. Lowry. Right? An acid in this case donates a proton. Okay, a base accepts a proton. Okay, so when you look at it in those terms, you got the acid reacting with water and produces H3O plus A minus. Which way did the electrons go? Proton went from here to here. That's an acid. Which way did the electrons go? Well, when the hydrogen goes over here, notice it's only a plus charge. So the electron pair went to A to make an A minus. So an acid donates a proton And Lewis acid accepts electron pair. Okay, from the bond that was between A and H. Right? If you do it like this, like that, then both of those electrons go over here. So that means this, as an acid, accepts electron pair. So the base, of course, donates electron. That's how I keep it straight. Acid donates proton, accepts an electron pair. Now, the advantage to Lewis concept is that you don't have to have protons. You don't have to have hydrogens to have an acid-base reaction. All you need is to follow the electrons. So in order to be a Lewis base, the Lewis base must be able to donate an electron pair, right? So we look at these possible A through B, A through E. Okay. And we've got our first one is O2 minus. Can that one donate electrons? Oh yeah, readily. And so that works as a Lewis base. How about this one? NH2 minus. Yeah, it's got some extra electrons to donate. How about NH2 with 1 minus? Yeah, it still has some electrons to donate, right? So it works as a Lewis base. How about this one? This one is a little trickier. You have to remember when we drew the Lewis structure for ammonia, what did it look like? Had a hydrogen in the back, had a hydrogen here, right? We're looking at the structure, right? That trigonal pyramid. But what else did it have? It had a lone pair above that nitrogen. That can be donated. So that's an electron pair that can be donated. That's a Lewis base. And then NH4 plus. Well, in order to do NH4 plus, we had a hydrogen up there. Now you have no more electron pairs to donate. This is the one that cannot be a Lewis base. All right. Now, 26. Let's make room in here. I'm going to leave that other stuff up here for our reference purposes. 26. All right. Which of the following species cannot be a Lewis base? All right. So we have these possibilities. N3 minus. All right, we've got lots of extra electrons there. Got extra electrons here, got extra electrons here, got extra electrons here. Oh. And that's the same answer. Right. That one cannot be a Lewis base. Oh, excuse me. I was in the wrong one, wasn't I? I was doing 26 over again, and you didn't say anything. Just sit back there and giggle at the instructor. All right, 27 then. Which of the following cannot act as a Lewis acid? Okay. Which one cannot accept an electron pair? Okay. What do we have to choose from? Well, we got these positive ions, right? They can accept electrons. All three of these can accept electrons. They're good. How about this one? Yeah, they can accept electrons. This one? Nope. No more electrons for this one. Why? We have to look at the electron structure of hydrogen. It starts off at 1s1, right? So it's got room for one more electron. And that's what this one is. Right? There's no more room for electrons there. So it does not act as a Lewis acid, cannot accept electron pairs. All right. And I threw 28 out. I can't remember why. It was a stupid question, I think. About 30. We still, no, we're off of Lewis, so I'll erase this stuff. Number 30. Given the following values of pKa, determine which is the weakest base of the answers listed. All right, so we got these possible bases: ClO2 minus, ClO, HCOO minus, and F minus, and Cl minus. All right. Now, if we didn't have this one right here, which is the result, this is the conjugate base of what? HCl, which is a very strong acid. It completely dissociates into these. That means this is a very, very, very weak base. Right? And it's not in the list, but it's in the possible answers. So the weakest base comes from the strongest acid. These guys are all weak acids. If you add a hydrogen ion to them, that's a weak acid, weak acid, weak acid, weak acid from a strong acid. This one is the weakest base, that chloride ion. It's the very weakest base out of all of those. It's a trick question, right? Pay attention to the answers because the rest of it is blue smoke. Oh, well, not actually. What that tells you is those pKa's tell you that these are all weak acids. And if you go to a strong acid, you're going to get a weak base, weaker than any of these other acids. Let's see, do we have any more in chapter 14? Yep, we got this one. Here we go. All right, 38. Doing on time. Okay, we've used up an hour so far. Carbonic acid is a diprotic acid, H2CO3. H2CO3. All right, that's the same stuff you have in pop. They dissolve carbon dioxide in water and it makes carbonic acid. Okay, the Ka1, which would be what? The first dissociation, HCO3. Right? And this Ka1 is equal to 4.2 times 10 to the minus 7. Okay. Ka2 would then take that polyatomic ion and dissociate the other proton. Which is 10 to the minus 14. Oh, no, it's water. 4.8 times 10 to the minus 11. Okay. The ion product for water is 10 to the minus 14. Okay. So what we're saying there is this one, well, let's be consistent. I'm just using the simplified version. So this Kw is 1 times 10 to the minus 15 at 25 degrees. What's the hydroxyl ion concentration of the solution that is 0.18 molar in sodium carbonate? All right. We're given a, let's see, sodium carbonate, which does what? All sodium salts are soluble. So what it's going to produce is 2 sodium ions plus a carbonate ion. And this one is 0.18 molar, correct? Right. So what does that make carbonate? That makes carbonate 0.18 molar. All right. If this is 0.18 molar, which side of this reaction is favored? With that value at 10 to the minus 11, this side is favored. And once this is produced, which side of this one? That one is favored. And 10 to the minus 14 is the Ka for water, which means what effect is water going to have? Well, actually what we need to do is determine determine this concentration. I think that's where I'm headed. Let me be sure. You know what? I'm barking up the wrong tree. If we have this concentration in here, what reaction is actually determining the pH? The pH is actually being determined by this reaction. H2O plus CO3, 2 minus, yields HCO3 minus plus OH minus. That's the reaction that is calculating the pH. All right, so we can set up an ice table with that one. Well, actually, what we're going to need is a KB for this reaction. Right? So we're looking at this one right here. So what's the KB for this reaction? It's based upon this conjugate base. So the KB for this reaction is 10 to the minus 14 divided by 4.8 times 10 to the minus 11. Let's go ahead and calculate that. And 4.8, this is 2.08 times 10 to the minus 4. That's the KB for this reaction. We'll need that in just a minute. Okay, what's the initial concentration? Well, water doesn't count. The initial concentration here is 0.18 molar, right? And we're saying that we're starting off with nothing there, essentially nothing there, right? Because there will be a little bit there because of the water. But what's the change? Well, we know it has to go that direction. So how many are we going to lose here? We're going to lose some there, and it's going to show up over here. Right, so 0.18 minus X and X. Okay. All right, now I need some more room, so I'm going to have to, let's see, I'm going to erase this one. Put it over here. All right, so that KB value is 2.08 times 10 to the minus 4, right? And that's equal to X times X, right? Product, this one times this one, divided by this one. 0.18 minus X. All right, the question is that X big enough? Right, with 10 to the minus 4, is it going to produce enough X that significantly approaches the value of 0.18? And since the value is 10 to the minus 4, it's probably not going to make a lot of X. We're not going to lose a lot of X from this side. So we should be justified in saying X squared over 0.18. So X then is the square root of 0.18 times 2.08 10 to the minus 4. Which is 3.75 times 10 to the minus 5. So X, or the hydrogen ion concentration, the hydroxyl ion concentration, should be the square root of that value. 6.12 times 10 to the minus 3rd molar. Let's see, what was the question? That's the question. So A should be the answer. Now, if you want to be sure that this is correct, you would do a compare with 5%. Right. In order to do that, you would take this X, put that X back in here, and solve for X again. Well, actually, no. What you would do is put the X in here, here, and here, and calculate the K value and compare it to that one. So if we did that, let's take that value and square it. Let's see. Okay. And then divide it by 0.18. And 6.12 exponent minus, divide that into 2.1. Now we're saying the Ka calculated is equal to 2.16 times 10 to the minus 4. Right? Is that 5% or within 5% of that value? Well, what's the difference? 0.08, 0.08, and 2.08 divided, and then 100 times that. We have 3.8%. Right, so we're within 5%. We calculate the K based upon this value and compare it to the actual K, then we're within 3.8%. So we're justified in making this assumption right here. Okay, did I lose anybody? That's why I put this note at the bottom. Compare KB1 and KB2. Well, since we calculate the KB by dividing the Ka into 10 to the minus 14, all we have to do is say the controlling reaction is the one with the smallest Ka, which will give us the biggest Kb. So this one is the smallest Ka out of these two reactions. And that controls the pH. That's why we only used this one. And we didn't combine the two. All right, that was 38. Okay, 38, 39. Right. Calculate the pH at equivalence for the following titration. 0.1 molar. 0.1 molar. It's covered up. Okay, let me scoot it over a little bit. 0.1 molar HOCl. Okay. HOCl plus sodium hydroxide. And that's being titrated to give us sodium hypochlorite. plus water. Okay, and we've got both of them are 0.1 molar. And we're given the Ka. Yeah, is that the Kb? Let me be sure. Yeah, the Ka of HOCl is 3.5 times 10 to the minus 8. Okay. The way to approach this problem is in two steps. One is you do the stoichiometry, and then you work backwards with equilibrium. Okay. So all we've got is concentration. But if these are stoichiometrically equal, then we can pick any volume we want to determine the concentrations. So let's just say 100 mils each. How about that? That'd make it easy. So if we have 100 mils of this and 100 mils of this, right? And at equilibrium, at equivalence, we're going to use up all of this and produce that. Right? So we can pick either one of these. It doesn't matter. Like 100 times 0.1 is what? Is 10 millimole. So that produces 10 millimoles over here. All right. All right, so that is the stoichiometry. We found out how much hypochlorite is produced at equivalence. So now that we know that, what's the reaction that is in equilibrium? Now we've got this molecule in solution, OCl minus. What's it going to react with? It's not going to go back with any of these. It's going to react with water. And that produces HOCl plus OH minus. Okay, now this is the equilibrium. All right, so initially, what do we have? Well, we've got 10 millimolar. We've done millimole before, haven't we? Okay, 10 millimolar divided by what volume? Well, we're adding 100 plus 100, so it's actually 200 mils. So millimoles divided by milliliters is molarity. And that's 10 divided by 200. I should be able to do that in my head, but I'm not feeling too spry today. So this is 0.05 molar. Okay. And we're starting off with essentially, well, nothing there and essentially nothing there. Okay, what's the change? Well, the change is we're going to produce some of this in a 1-to-1 ratio. And we're going to lose a little bit of this. So we got 0.0500 minus X. That's correct. And then X here. Okay. So what we need to know is the Kb. We got the Ka. So the Kb is going to be equal to 10 to the minus 14 divided by 3.5 times 10 to the minus 8. So 1 exponent 14 and 3.5 exponent 8 is 2.86 times 10 to the minus 7. Okay. So now the this value, the Kb, is equal to x squared, right? X times x divided by 0.0500 minus X. Now we have to ask ourselves, is X going to be big enough? Right? Or is it small enough that we can eliminate it? And 10 to the minus 7 tells me that X is going to be significantly smaller than 0.05. That means we should be able to say this, X squared over 0.050. Okay. So X then is going to be the square root of that value times this value. (1.43 times 10 to the minus 8), and X, which is the hydroxyl ion concentration. Just take the square root of that. 1.20 times 10 to the minus 4 molar. If that's the hydroxyl concentration, we want to calculate pH. So the pOH is the negative log of that value. Let's take the log of it, change the sign. 3.9. And the pH then would be 14 minus 3.9. Oops. Let's try that again. 10.1. That's our pH. At equilibrium. Now, why would we want to know that? Well, if you've got a whole lot of these titrations to do, you don't want to have to do each one of them to equivalence to find out what the actual concentration of each one is. We're given the concentration here. But if we have an unknown and we're titrating it to find out what the known is, what the unknown is, then we want to know what pH are we when we reach equivalence. And we can do it with a pH meter, but that takes a lot of extra effort. If we have an indicator that will change color near pH 10.1, then we can use the indicator and just knock out 100 of those in a day, easy. So knowing the pH at equivalence is important if you're going to do a lot of these titrations. All right, that takes care of chapter 14. Now we're going to stop the share and go to 15. All right, let's go here and then here, excuse me. And there's 15. Okay, so now let's share that screen. That's chapter 15, yes. Let's blow it up some. Yeah, we can see the whole thing on there. Let me move it over just a hair. It's like it's sliding off the screen. Okay. So let's make room and switch chapters. Okay, 15. All right, the first one in chapter 15 is 4. We want to take a look at. Let's see. Okay, well, we'll just take them one at a time then. A weak acid HF is in solution with dissolved sodium fluoride. Weak acid is in solution with dissolved sodium fluoride, which means what? It means, let's do this. It means that we've set up a potential buffer situation. That's from sodium fluoride, and this is the acid. There we go. Okay. If hydrochloric acid is added, which ion will react with the extra hydrogen ions from the hydrochloric acid to keep the pH from changing? Well, if you got this in solution, like chloride is a spectator. We're interested in that. So where is this one going into this scenario? It's going in right here, which means it reacts with fluoride. And when it reacts with fluoride, which weak acid, strong base, this strong base is going to suck up some of those hydrogen ions and shift the equilibrium back to the acid. So the reaction is between the hydrogen ions and the fluoride ions in order to maintain the pH. All right, we've got five coming up. All right. Which of the following is true for a buffered solution? Well, this is kind of on the same lines as 4. The solution resists change in hydrogen ion concentration. Now, is that true? Yep. It doesn't prevent change, it resists change. The solution will not change its pH very much, even if concentrated acid is added. Yep, that's true. That's the nature of a buffer solution. C, the solution will not change its pH very much, even if a strong base is added. That's also true. Any hydrogen ions will react with a conjugate base of a weak acid already in solution. And we just proved that. The conjugate base of hydrogen fluoride is F-. And the hydrogen ions will react with that in solution. So all of them are true. All these statements are true. Right. Let's see, 8. How do the pHs of the buffer solutions compare? All right. Let's see. Is that based upon? Yeah, it's based upon this thing up here. All right. Solution 1. Solution 1 versus solution 2. Solution 1 is 5 molar acetic acid and 5 molar acetate. So we got 5 molar acetic acid, B2H3O2, and 5 molar acetate ion. That's what that's saying. Sodium acetate, right? Sodium is a spectator. So we have equal concentrations of these, which means what? We're right smack dab in the middle of the buffer zone. The best place to be for a buffer. How about solution 2? Well, the ratio is the same. Right, 0.050 molar C2H3O2. The ratio is the same, but the buffer capacity is not the same. All right, so 8, we want to say, how do these compare? Well, the pH of buffer solution 1 is greater than? No. pH of 2 is greater than 1? No. pH of buffer solution 1 is equal to that of buffer solution 2. And D is just stupid. We can determine without the Ka values. Right? So the pHs of these two are equal. Because of the ratio. Remember Henderson-Hasselbalch? pH equals pKa plus log of the conjugate base divided by acid. So if the ratio is the same, the pH is going to be the same. The ratio is the same, 5 to 5, 0.05 to 0.05. pH is exactly the same for these two solutions. All right. Oh, we're getting into another one now, 9. Which of the following is the net ionic equation for the reaction that occurs during titration of nitric acid and potassium hydroxide? What's the net ionic equation for any acid-base reaction? Protons, hydroxyls, make water. That's the net ionic equation for any acid-base reaction. All right, how about 10? In the titration of weak acid HA with 0.1 molar sodium hydroxide, the stoichiometric point is known to occur at a pH value of approximately 10. Okay, so we're reacting this acid, whatever it is, with this base, and the stoichiometric point that produces that salt plus water, the stoichiometric point is at pH 11. No, excuse me, 10. Right? Yeah. Which of the following indicators would be best to use to mark the endpoint? Right, that's the stoichiometric point. Which one is closest to the endpoint? Well, all you need is the Ka for the indicator. The Ka will tell you when the color changes. So for indicator B, it looks like it's the closest one. Right? Indicator B is the closest one to 10. It's a little bit high, but when you're titrating an acid, an unknown acid amount with a known base, it's best to have the indicator change colors above the pH. If you go the other way, right, if you titrate an acid against a base, then you want to go the other way and have the indicator below. So 9 would be better for, 9's not there. If we were doing it the other way, titrating a strong acid with a weak base, then we would want to go indicator change at pH 9. Now, why is the Ka so important? It goes back to Henderson-Hasselbalch. Right? And in this one, we have the indicator part base and the undissociated indicator like that. So the change of color is based upon the balance between these two. And remember what that pH unit change is that we can detect. This is a physiological effect. It's plus or minus 1 pH unit. So how do you get 1 pH unit out of this? Well, if this is 10 to 1, then the pH change is plus 1. If it's 1 to 10, let's see. Do it like this. 10 to 1 would be a plus 1 pH, and 1 to 10 would be a minus 1 pH. So if your pH is within plus or minus 1 pH unit, that's where the color change occurs. So if we know the Ka, we know that the color change is going to occur for this one, where it's 10 to minus 11. We know the pH change is going to be between 12, 10, and 12. Okay. That's straight out of the lecture and your book. All right. 13. Which of the following solutions would be described as a buffer solution? Okay. What do you need for a buffer? You need a weak acid and its conjugate base. And as close to 1-to-1 ratio as possible. So how about that first one? Acetic acid and HCl. Well, you get two acids, right? You can't form a buffer with two acids. How about acetic acid and sodium hydroxide? Well, 0.25 molar acetic acid, 0.25 molar of the acid, and 0.2 molar of the base is going to do what? It's going to put you very close to the equivalence point. You're nowhere near the buffer zone. Right? So that can't be. How about 0.15 sodium bromide, 0.15 sodium, oops, that's not right. Yeah, sodium bromide, sorry. And 0.2 molar HBr. Well, the ratios are good, but the acid's not. That's a strong acid, right? It's not going to work. You got to have a weak acid to produce a strong conjugate base. So, wait a minute. Which of the following solutions would be described as a buffer? Now, why does it say B? If we react, let's go back to this one. C2H3 or CH3COOH. Did I show you that one before? VOOH. That's another way of writing acetic acid. Which would be, it gives you a little information about the structure. Right, there's your CH3, and you have the other carbon, and you have an oxygen, you have O and H, and that is the acidic hydrogen. Okay, if we add these together, this is going to consume some of this acid and turn it into 0.2 molar C2H3O2 minus and leave behind 0.05 molar acid. I guess you could call that a buffer, but it's not a very good one. Right? Because what's the ratio? 0.2 divided by 5 is 4. So this ratio here is 4-to-1. And what's the log of 4? Curious. 0.6. Right, so that's 0.6 pH units. Yeah, it might work. Okay. So I guess this one is possible. Not the best buffer, but it would work. How about, did we do D already? Or we found the answer, but not a good answer. 0.25 ammonia and 0.15 sodium hydroxide. Those are two bases. Right, that can't work. And HCl and NOH, right? Strong acid, strong base is going to be neutral. Right, so that can't work. Right, so I guess pick the best answer. That would be the best one. Although it's not a very good one. All right, 14. Maybe 14 is better. Give us some better choices. Let's see. A, B, C, D, E. Is A, what does A have in it? There's nothing. It's got a salt of chloride, but chloride is not a strong base because HCl is a strong acid. Right, so that one can't be it. I throw that one out. Oh, now we have acetic acid and sodium hydroxide, equal concentrations and roughly equal volumes, which means B is going to be at the equivalence point or just past the equivalence point. Right? So that one can't work. Right? You're not in the buffer region there. C, 50 milliliters of 0.1 molar acetic acid and 25 milliliters. There you are. If you got half the equivalence volume for that, for C, would be equal to 50 milliliters of base. Half the equivalence would put you right in the middle of the buffer zone. So C is the best answer so far. 0.1 molar acetic acid and 0.5 milliliters of 0.0001. No, that's not enough base. D can't work. 50 milliliters plus, no, you can't add two, can't put two acids together and make a buffer. C is the best answer. And it's based upon the titration curve, right? Added base and pH for a weak acid starts off like this, goes like that, goes like that. This, there's your equivalence point, right? So equivalence volume, and this is right, 1/2 equivalence volume. That's the best point for a buffer right there. All right. Now it's 14. And let's see what's next. We're waiting on our lab partners to arrive. Okay. 19. This one might take some work. Maybe not. Consider the following indicators and their pH ranges. Assume an indicator works best when the equivalence point of the titration is in the middle of the indicator range for which of the following titrations. All right, I think this one's going to take some doing. Yeah, I was afraid of that. Okay. So what we need to do is find the equivalence point for each of these reactions. Okay. Where would be the equivalence point for nitric acid and KOH? Strong acid, strong base. It would be pH 7, right? Strong acid, strong base is neutral. So equivalence is pH 7 for the first one. That was mercifully easy. How about aniline and HCl? All right, so if we get aniline, let's see, let's just say HA for, no, that's not right. Aniline's a base. So let's just say, there's the aniline molecule. And if we react it with HCl, what's that going to do? Well, it's going to add a proton to A, aniline, and give us chloride. Okay. So the Kb for aniline is, let's see, am I approaching this right? Oh, here we go. All right. So your work problems approaches this just calls aniline B. And then we get HB plus. Okay. So what we're looking at is the KB for this one, which means what? Well, KB says that B plus water yields plus OH minus. Okay. So when we reach equivalence, once we've established equivalence, now we've got this possible reaction. We have water. We have water can do this. H plus OH minus. And this KW is 10 to the minus 14. What's this KB? All right, well, we're given the KB, right? Where is it? KB. 3.8 times 10 minus 10. 3.8 times 10 minus 10. Right. So this one is going to dominate reaction. We don't have to consider water. So once we've got equivalence with 0.1 molar aniline, then if we go again with 100 milliliters, right, of 0.1 molar aniline, then we're going to end up with no, that's not right. Because once we've reached equilibrium, once we've reached equilibrium, then we're going to have HP plus water yields B plus H plus. So we need Ka here instead. Ka equals 10 minus 14 divided by that. So this would be 2.63 times 10 to the minus 5. Okay. Now if we go back to our equilibrium situation, right? If we're starting off with 10 millimolar divided by 200 milliliters, which is 0.05 molar. Okay, and 0 here and 0 here. So we're going to end up with, we know what the change is going to be. Equilibrium is going to be 0.05 minus X. Might as well put them all in there. Plus X. Because each of these calculations is going to follow the same process. Then this is going to be X. So now 2.63 times 10 to the minus 5 equals X squared over, and with that small value, we're going to say 0.5. Right? So X is going to be the square root of 0.05 times 2.63. 5 times that is 1.32 times 10 to the minus 6, and X equals square root of that. 1.14 times 10 to the minus 3. But we need to know the pH. X is the hydronium ion concentration. So we need the negative log of 1.14 times 10 to the minus 3. Which is 2.94. 2.94 pH for this one. Okay, that was B. Let's see. Methyl red. We're looking at methyl red, which is 4.8 to 6.0. We want to use this indicator, 4.6 to 6.0 pH. All right, so B won't work. right? That was going to change at 2.94. Did I do that right? Yeah. Okay. All right, so we did that one. This looks like a good bonus question because it's going to take forever. How about C? Ammonia and HCl. So we got ammonia plus HCl yields NH4 plus Cl minus. And stoichiometry here will be the same thing as above. Right? So we're gonna get, this is our equilibrium reaction plus H2O yields H3O plus NH3. All right. So we know that at equilibrium, we're going to end up with 0.050 minus X. This is going to be X and this is going to be X. So what we need is the Ka for ammonia. So the Ka for ammonia is 10 to the minus 14 divided by 1.8 times 10 to the minus 5. So what's that? 8. Right. This is 5.56 times 10 to the minus 10. Okay. So we're going to have 5.56 times 10 to the minus 10 equals X squared. And we're going to say, we're going to drop that X out of there because this is so small. 0.050. X is going to be the square root of 0.05 times that. 2.78 times 10 to the minus 11 square root. It's 5.27 times 10 to the minus 6. And that's the hydronium ion concentration, right? So pH is going to be the negative log of that value. 5.3. 5.3. I think we got a winner. Right? The pH at equilibrium is going to be 5.3. That's right in the middle of methyl red. Okay, we could do the others, but in the interest of time, right? It's the same process, right? You go to equilibrium, and then you take the product of equilibrium and then put it back into its, you go stoichiometry, then you take the product of stoichiometry and go to equilibrium, right? HF would react with sodium hydroxide to produce F minus. Now what you need is the Kb. We got the Ka for HF, we need the Kb. And then you would end up with the same type of calculation, only with HF, you would end up with hydroxyl ion concentration, POH, then you convert it back to pH, and that would, you'd compare. Everybody asleep yet? You have to get excited about it, otherwise it'll bore you stiff. All right. Let's see, 23. Um, 50 milliliter solution of 0.035 molar hydrocyanic acid, that Ka is titrated with 0.033 molar solution of sodium hydroxide as a titrin. What's the pH of the acid solution after 15 milliliters of titrin have been added? Okay, this one doesn't go to, we don't know, but it probably doesn't go to stoichiometry, the stoichiometric point, because they're telling us it's an acid solution. So that means we start off with the acid, we add a little base, and it's still acidic. All right. So what we've got is hydrocyanic acid. You have to be able to write that. And then we're titrating with sodium hydroxide. Okay, and that's going to produce sodium cyanide in aqueous solution, which means it's broken up. It's completely soluble in water. Okay. So what we're given is 50 milliliter solution of 0.035 molar. 50 milliliters of 0.0350 molar. And then we have 15 milliliters of sodium hydroxide solution at 0.0333 mole. All right. We have two reactants here with definite amounts. We need to know which one's limiting. And these values here, these concentrations are very close together. So what we can say is that's still got a whole lot more acid than the base added. So this is going to limit the reaction. It's going to use up all of that sodium hydroxide. All of it's gone. Right. So if that's the case, then how many millimoles of this one and how many millimoles of that one are we starting with? So 50 times 0.035 is 1.75 millimoles of acid. And 15 times 0.0333 is 0.50 millimoles of base. Okay, so we're still talking stoichiometry here. This is stoichiometry step. All right, how much sodium cyanide is produced? Well, we're going to use all of this up, and that's going to produce 0.5 millimole of cyanide ion. And what's left over here? Well, it's a 1-to-1 reaction, right? So we're going to have, let's see, 1.25 millimole of hydrocyanic acid. So this is our starting point for the equilibrium. Okay, so what equilibrium are we looking at? To be sure I'm not stepping on my tongue. Yeah, we're still looking at the acid reaction. And so now that we have that done, we're going to the equilibrium. So hydrocyanic acid will produce hydrogen ions plus cyanide ions. And now our starting point, our initial, is hydrocyanic is 1.25 millimoles by what volume? Well, we had 50 plus 15 is 65 milliliters, right? 65 milliliters. Millimoles divided by milliliters is molarity. And on this side, we have hydrocyanic acid, which is 0.5 divided by the same volume. Okay, so let's see what the concentration is there. .25 divided by 65 is 1.92 times 10 to the minus 2 molar. And this concentration is 0.5 and is 7.70 times 10 to the minus 3. Okay. Now, what's the change going to be? Well, what we're saying is that this reaction is going to go that direction because we're starting with this amount and that amount and no hydrogen ions. So we're going to lose, and this is lose some of this. We're going to gain some of that and gain some of that. So now we have, at equilibrium, we have 1.92 times 10 to the minus 2 minus x, x here, and 7.70 times 10 to the minus 3 plus x. Okay, that's our equilibrium situation. All right. The worked problem uses the quadratic, and that's perfectly all right. But I need some more board space here. Let's see, I can put it over here. Let's put the equilibrium situation over here. Now, what we need also is the Ka for acetic acid. I mean, hydrocyanic acid. And actually, I skipped a step. When we're looking at the equilibrium here, does this control the pH or does water control the pH? Because that's the only other competing reaction. Well, Ka is 10 to the minus 10. And Kw is 10 to the minus 14. So this controls the pH. Right? It's 4 orders of magnitude stronger. So water will have no impact on the pH. All right, so we're going to use 6.2 times 10 to the minus 10. 6.2 times 10 to the minus 10 is equal to x times 7.70 times 10 to the minus 3 plus x divided by 1.92 times 10 to the minus 2 minus x. Okay. So simply stated, this x times that x is going to give us x squared, which means we've got a quadratic on our hands. Right. Here's the other thing you can do. We can do successive approximations. Now, how would we do that? Well, in order to make successive approximations work, you need to eliminate the possibility of an x squared. So we would definitely get rid of that x. But if we do that, then this would go on that side, x, and this would still be an x on that side. So you have the possibility of another x squared. So what you would do is eliminate both of these x's right here. And this would be 6.2 times 10 to the minus 10. Now you can use the quadratic if you want to. I have no objections. And this is approximately, we're saying 7.70 times 10 to the minus 3 divided by 1.92 times 10 to the minus 2, like that. And then solve for x. Okay, we're doing the work problems for this one uses the quadratic equation, which is perfectly all right. But I'm trying successive approximations. The first approximation is not going to be correct. I know that right off the bat. So 6.2 exponent 10, and then times 1.92 exponent 2 minus, and then divided by 7.7 exponent 3. So this says x equals 1.55 times 10 to the minus 9. Right? So the next thing you would do is substitute this x for that x and that x and recalculate x. Okay? So that means now we're doing 6.2 times 10 to the minus 10 equals x times 7.70 times 10 to the minus 3 plus 1.55 times 10 to the minus 9. And this one would be 1.92 times 10 to the minus 2 minus 1.55 times 10 to the minus 9. That doesn't look like it's going to have much effect, does it? Well, let's see what this is. 1.92 exponent to this, and then 1.55. Subtract those. This is still, that's what I thought. It'd still be that number. You know what? What was the question? What's the pH? Okay. These values are so much smaller than those, I don't think it's going to have an impact on them. So let's take this value as our hydrogen ion concentration at equilibrium and calculate the pH and see what happens. Right? So the negative log of 1.55 times 10 to the minus 9 equals what? Let's see, let me get back up here. There we go. Let's see, log of that, and then change the sign. So this says 8.8. That's it. So you don't have to use quadratic. That's what this shows, right? If we do successive approximations, we get an x that's so much smaller, right? That's the assumption that we make when we eliminate the x's in our other calculations. We say x is so small, it's not going to affect this value. Well, we just proved it, right? If we say x is small, and then we calculate x and we say, okay, right, there it is, right? 10 to the minus 3, 10 to the minus 9, it is so small. 10 to the minus 2, 10 to the minus 9, very small. So we're justified in eliminating those two. And then in order to compare the 5% rule, you put these values back in there, and notice we end up with essentially the same value, right? It's so small, the difference is so small, percentage is irrelevant. It's such a small value. Did I lose anybody? What I was trying to do, right? The review document uses quadratic equation. I tried to do successive approximations by eliminating that x, calculating what the x is, then putting it back in and recalculating this x, putting x in there and x in there, leaving that one alone. And what I discovered was that putting this x in here doesn't change those values at all. So we would have been justified in calculating x simply by eliminating those two x's and just going for that x. Okay? All right. I think that horse has been beaten enough already. We'll go on to the next one. But overall, the procedure was the same. You do the stoichiometry first, and that gives you a starting point for your equilibrium. What you have to do is decide what equation determines the equilibrium. All right, 25. A certain indicator has a HIN has a pKa of 9, and the color change becomes visible when 7% of it is IN minus. At what pH is the color change visible? All right. Let's say we have this indicator, and it has pKa. I'm just putting the stuff we know up here of 9.00. And the color change becomes visible. Say color change when 7%. 7% of it ends up over there. That's when the color change becomes visible. Okay. So the reaction we're looking at is this one in equilibrium with that one and this one. There we go. Now we're going to need the Ka. So we might as well calculate the Ka from this value. How do we do that? Well, if this is the negative log of the hydrogen ion, excuse me, sorry. This is the negative log of the Ka. There we go. So Ka then is equal to 10 to the minus pKa. Right? Because this is base 10. Move the negative over here and say 10 to that power equals this. So that would be 10 to the minus 9. Which is that right? Yeah, 1 times 10 to the minus 9. Correct? Yeah, that's right. Okay, now if we set up our ice table, we want to know at what pH is the color change visible. Well, we need to find out with that value right there. Right, so our initial situation is, let's see, do I invent a concentration? No, there's no need. Sorry. We're not going to use the ice table. Right? That's too much sugar for a dime. We're going to use Henderson-Hasselbalch. In fact, if we use Henderson-Hasselbalch, I don't need the Ka. pKa plus log of In minus over Hn. I was making it harder than it needed to be. So what's the ratio here? Well, 7% of it is now In minus, right? Which means 0.07. What is Hin? 9.03, right? Well, let's do percent. Right? If you start off with 100%, now 7% of it is over here. That means 93% is left over, correct? That's better. 7% is here, left behind is 93. So this is 7 and 93. Right? That's when the color change becomes visible. All right, so what's 7 divided by 93? This is 7.53 times 10 to the minus 2. And we need to take the log of that. So the log is minus 1.12. And this is 9. That's not the right. Yes. Put those together as your pH. 7.88 pH. Now 7.85. Calculation error. Now, if you come up with that and you show me this result, let's see if I did that right. Oh, you know what? Seven percent is in In minus. I'm not so sure that that's calculated correctly. If 7% of it ends up over here, then what's left behind? 7% is here, 93% is over here. I think this is a better answer, 788, rather than 785, because the worked problem says that this whole value right here is 7%. Right? or 0.07 rather than 0.0753. That's why the work problem is different. It produces 7.85 and I get 7.88. So if a problem like this shows up on the exam and you calculate it this way and it doesn't exactly agree and you say none of these, then all you have to do is show me your work and I'll give you credit. That shows your brain's working. Yeah, I think what I was doing there was taking the word of whoever created the problem, and I think they're wrong. Either that or they stated the problem incorrectly. They meant to say something else. If they said the ratio of IN minus to HA is 0.07, then I would take them at their word. When they said 7% is converted, that means 93% is left behind.
I would be document is 7.8.
Oh, okay.
I'm not sure.
All right, this is an older version. Yeah, take that one. Yeah, that correction was made after this one was created. Okay. And which means I need to go in here and make the correction on the work problems, because the work problem comes out 7.85. I think that's the last one. Oh, no, there's more. Oh, there's more that aren't in the work problems. Oh, okay. We need to do these then. That's probably why I highlighted them, because I don't have them in the work problems. So let's do these. In the figure below, the pH at first hydrogen equivalence is approximately, all right, so we're working from this diagram right here. So let me shrink it so we can see more. So what's the pH at first hydrogen equivalence? Right. If you're starting off with an acid, that means you're going to be no base added. You're going to be way down here in this low pH. So what's the pH at first hydrogen equivalence? Isn't that the question? Yeah. And look at our choices: 1.2, 2.3, 602, 969, and 11.85. So where's the first equivalence occurring? Right here at C. That's the first equivalence point for this polyatomic ion. And that's close to, the closest answer to that one is 6.02. And 27 is based upon that same graph. The acid would best be used in a buffer near pH what? The buffers are going to be either B or D. All right? That's where the curve is flattest, B or D. B is about 2.3 or 2.4 pH. And D is about 9.6 or 7. So where's the closest one to that? Let's see. Closest one to that is 10. Right? That would be a possible buffer. Notice it's just a little bit higher than the exact center. Okay? That's your buffer zone. So this weak acid has two buffer zones, either in this range or in this range. That's a diprotic acid. A triprotic acid like phosphoric acid would have three possibilities. That's why you find that biological buffers that are used for to culture cells and to work other biochemical problems is very often based upon phosphoric acid, because you have the possibility to adjust the pH to either the first, second, or third buffer zone. Questions?
So it's either second equivalent point.
Yes. Yeah, E would be the second equivalence point for the second hydrogen. Yep. That's exactly right. And that's it. I think I threw those in there because we hadn't talked about it, and I wanted to be sure and get that into the discussion. Okay.